All right, let's do this last example. So we have a particle that starts at x equals 0 and moves along the x-axis with velocity. So we're talking about having a rate given by the velocity is t squared for t greater than or equal to 0. T is in seconds. The velocity is in, feet per second. And we're wondering how many feet has this particle traveled during the first 3 seconds. So we're going to use our rectangle approximation methods. So this is the right-hand side of a parabola. Let's draw that. And we're talking about the first 3 seconds. So at the first second, we're at 0, 0. 1 second, we're at 1, 1. 1 squared is 1. At 2 seconds, we're at 2 squared, which is 4. And at 3 seconds, we're at 3 squared, which is 9. So it makes sense, since we're talking about a 3-second interval, let's make ourselves 3 rectangles, one for each second. So rectangle 1, 2, and 3. All right, so we already know how to do our left and our right ram. So let's just do that quickly. I'm actually going to start with the right ram. So each one of these rectangles, this is at 1, 2, and 3, has a width of 1. So 1, 1, and 1, we're doing our ram. We know that we're going to be multiplying all 3 rectangles by the width, like we saw in our last example. And we only have to add the heights. We factored out the 1. So my right-hand height for my first rectangle is an overestimate. The height at 1 squared is 1. Our second rectangle has a height at 2, which is 4, a big overestimate. And our third rectangle has a height at 3 squared, which is 9. 9, 10, 11, 12, 13, 14. 14 feet is our right ram overestimate. Easy peasy. So let's do our left ram now. Same process. All 3 rectangles have that same width of 1. And now I am adding our values from the left side. Now this one's a little bit weird. Our first rectangle still has that width of 1, but the height here on the left, which is at 0, is a height of 0. Don't actually have a rectangle there. It's completely flat. The height on the left is 0. So I am adding 0. Rectangle 2, the left-hand side of rectangle 2 is when t is 1. 1 squared is 1. And the left-hand side from 2 to 3 is 4. So my left ram underestimate is 5 feet. Now, we've already seen our third rectangle approximation method. We did it in the last 2 videos, and that's our A ram, our average ram. So if we average these, we're averaging our over and underestimate, 14 plus 5 divided by 2. And our average estimate is 9.5 feet. So 9.5 feet is certainly a better estimate than the lower estimate of 5 or the upper of 15. Now here's where we're going to get a little trickier. And this is the one that most students have a hard time with, our last rectangle approximation method. So this one, if you haven't drawn any of these with me, this one is important. Our last method is going to be an M ram. M standing for middle. We've done left, we've done right. Now we're going to do the middle. Okay. We have the same 3 rectangles. This is the first thing that kids have to realize so they don't get this wrong. We have 3 rectangles. Each of those rectangles still has a width of 1. We're going from 0 to 1, width of 1, 1 to 2, width of 1, 2 to 3, width of 1. But this time, when we add our 3 heights, we're not taking the height from the right or the left, we're taking the height from the middle of the interval. So between 0 and 1, the middle is at a half. That means the height of the rectangle still goes from 0 to 1. That doesn't change. But the height of my rectangle is found in the middle, which means when I'm going to do that horizontal, that parallel top to the bottom, half the top is going to go left, half is going to go to the right. When I shade in that rectangle, can you see that what I'm doing is half of the rectangle is an overestimate, the other half of the rectangle is an underestimate. So in one rectangle, I'm splitting the difference between over and underestimate. The MRAM, put a star there. If we can calculate the MRAM, which we can't always, that will always be your best and closest estimate to the actual value. Now, let's be careful here. What is the height of the rectangle when x, or in this case, t, is 1/2? Well, my function is the x value squared. So 1/2 squared is 1/4, 0.25. Instead of 1, instead of 0, my height is 0.25. My second rectangle will be from the middle between 1 and 2. 1.5. Half the top goes left, half the top goes right. I'm over and underestimating at the same time. A little bit easier to do this in fractions. I have 1/2, 2 halves, that's 3 halves. 3 halves squared is 9/4. It's actually easier than getting the little fractions, doing 3 halves, 1.5, squaring it. Our last rectangle still goes from 2 to 3, but we want to find the height, half an overestimate, half an underestimate. I have 1/2, 2 halves, 3 halves, 4 halves, that's 5 halves. The height of this rectangle, t squared, 5 halves squared, is 25/4. Easy to work with the fractions here. 25 plus 9 plus 1 is 35/4, which now, if you want to put that in terms of a decimal, is 8.75 feet. I still don't know the exact number of feet that this particle has traveled in 3 seconds, but I can tell you that our very, very best estimate is 8.75 feet. Definitely no more than 14, Definitely no less than 5, but not even 9.5. 8.75 is the much better estimate. Very soon, we're going to be learning how to find the exact value that the particle has traveled. Okay, so we now have 4 rectangle approximation methods. These are called Riemann sums, named after the German mathematician Bernhard Riemann, 1826 to 1866, back before they had Xbox and they actually thought things through instead of, distracting themselves with the glowing box and the things. So Riemann sums will find the sum of the area of all of the rectangles, no matter how many rectangles we choose to use. Okay, very soon we're going to be learning how to find the exact value. See ya.